Hi everybody. Today I will be talking about in this fourth FVD tutorial. Um, I will be talking on geometric sections and dive loop drops for wing coasters. I'm not quite sure if that's how it's called, dive loop drop, but you guys know what I am talking about, of course. So let's go ahead and get started with FVD. As always, let's establish our properties. For friction, as always, 0.024. And for this particular hardline height, for this particular style of roller coaster, let's set the hardline height for 2.5, which is the actual hardline value for wing coasters. So let's just start. Okay, let's just start our station here. Of course, the wing trains are a bit longer than usual, so let's just make our station with 40 meters long, and our lift hill, let's put a total angle of 40. Let's keep the track radius for 15. I think approximately 60 meters tall lift hill should be fine. I like high coasters. Yeah. So first thing you guys have to be aware of is that geometric sections work differently from force sections. Let's just give a simple example. When you add a force section here, you have three parameters in which you can change for you to be able to shape your track in the way that you want. So those parameters are the lateral forces, which is represented by this green graph here, and then it comes the roll, which is represented by the red line here, and the normal force here. The geometric section works a bit different. Why? Let's delete it for now, and let's add a geometric section. In the geometric section, you see how the graph changed after I added a geometric section. For the geometric section, you also have three parameters that you can change to shape your track, but the difference is you're not actually changing the normal force or the lateral force. The only parameter which is in common with the force section is the roll, which is still in red. But the other two parameters are the yaw here in yellow and the pitch here in turquoise, maybe this light blue here. We're basically gonna use the pitch and the roll to shape our dive loop drop. Let's just play a little bit with it just for you guys to get familiar with what happens when you actually mess with them. So if you decrease, of course, pitch and roll and yaw are all measured in meters per second. In degrees per second. if you changed, like if you increase the pitch of your geometric section for a positive value, it's gonna give you something like this. It's pretty much the same of increasing the g-force value. But the difference is you're not actually adding a positive g-force for your track. You're actually just establishing a determinate speed in which your track is gonna go up. Like your track is performing something about 50 degrees per second going up. We can roughly say that like your track is going up in a speed of 50 degrees per second. But if you do the reverse, like if you establish a negative value for your speed, look what happened. Your track is going down in a speed of minus 66 degrees per second because you're changing your pitch. Of course, if your graph behaves like this, like a pump transition, the following segment that you could add after this one would maintain a constant pitch like this because you're no longer changing the pitch. So that should be something about like something nearly a straight section like this one because you're no longer changing the speed of the pitch. So let's just undo it and let's come back to our pitch value, which is 0. Of course, the roll works the same or pretty much the same, not exactly. If you change your roll, your track is gonna rotate like this. But actually, the main difference right now is that if you change the roll of your segments of your geometric section, the lateral forces are not gonna be 0 anymore, and that's one of the main reasons why I don't like to work with geometric sections in the whole track. So they are somehow easier to work with because you are actually shaping your track by adding, let's say, shaping parameters, not actually g-forces. But at the same time, you no longer have the control upon your lateral forces properly. Neither your vertical forces. Actually, you can control the vertical forces better by working with force sections. You can control the vertical forces by changing the pitch, but it's not as accurate as controlling with the force section. So you can see here that the section that we are playing with has a constant pitch, a constant yaw, and a non-constant roll. But what this roll changing is making on this section of the track is it's rotating the track around the hurt line value. I mean the hurt line height, like around this red line right here. That's why there is a horizontal acceleration which is equivalent to the lateral force, which is 0.745. Let's come back to 0. This is just for you guys to be familiar with how the geometric section works. And of course the yaw, I've explained the yaw previously in another tutorial, so if you change the yaw, it's gonna go either to your left or to your right, like this. Let's just visualize normal speed. Yeah, it's better than normal force, sorry. So you can see that if I change the yaw, It's gonna go to the left or to the right, like this. Now we can actually start our actual dive loop drop. We're gonna go ahead and delete the geometric section. And let's first of all establish a speed at the top of the lift hill, which is gonna be something around 3.0 meters per second. And I highly recommend you establish a negative pitch, so that the train will be able to kind of go downwards by gravity. So the original angle of the lift hill is 40 degrees, so by adding a curve of 46 degrees, you're gonna have a pitch of around -6 degrees. And then you can add a straight section like this. The length of your straight section depends on you, depends on what you think it fits better. Of course, I'm not sure if all wing coasters in real life have a standard straight section right after the lift hill before the actual dive loop drop, but I usually set it just for 10 meters. And of course, you're gonna deactivate the fixed speed, because this way the program is gonna assume that the last fixed speed section was this curve right here, which represents the end of the lift hill. So from this part right here, let's deactivate them. So from this part here, the train is gonna start rolling, just moving by gravity, by kinetic energy, no longer by the chain lift or something like that. Of course, there are some models where the chain lift goes until up here, I guess. But just in terms of example, let's just establish this straight section without a fixed speed, just for the train to have some time to gain some speed before the drop. So right after the straight section, we're gonna add the actual geometric section. For now, we're not gonna change the yaw, neither the roll. We're gonna put in dynamic mode so that we can increase the 3 sections at the same time. You can establish a length of about yeah, it's not length, it's period of time, but you guys understand what I mean. So let's establish a length of 4 seconds for this section. And what we're gonna do next, we're gonna deactivate the roll section and decrease the pitch section for halfway, which represents something about 2 seconds, and then we're gonna add a new subsection of pitch and lock it again. Well, this is a 80-degree roll, because the train is gonna, is that 80 degree? Yeah, it's I'm sorry, it's 180 degrees roll. So we will have to turn like this until this value up here changes to something approximately equal to 180 degrees. So we have 179. Yeah, that should be fine. Once again, let's just adjust the tension for the transition to be smooth. After adjusting the tension, you will have to go back to the speed of the roll for you to be able to adjust it. to 180 or something like that again. Yeah, like this should be fine. But what are we gonna do now? That looks pretty much like the beginning of the dive loop drop, but it's not quite equal. What we need to do here is decrease the pitch section so that the train will be able to go downwards and perform the classical curve that is performed on a dive loop drop. However, we cannot, yeah, that's what we're doing here, but look how the how the graph works here. For this time, we don't need a graph that performs a how can I express that, is like a bump transition, because we're gonna need a continuous changing of pitch. So we're gonna deactivate the quartic input cubic so that the change of the pitch is gonna be constant in a constant speed. And let's visualize the normal force just to make sure nothing is going above or below too much. Now we will have to increase the size of the section, so we need to lock the roll. I'm sorry, I just messed. Lock the roll and lock the yaw again, and increase the size of the pitch change. Well, now we have the pitch change increased a bit, but it's not quite equal to what we need. So we're gonna go ahead and deactivate the roll graph, and add a new section of roll, and then a new section of pitch, and once again activate lock. When I say activate, just assume that it's lock the section. By what I'm saying here, I would say that if we continue this section without a change, the train is gonna go into the ground, and that's not what we want. So when you notice that the radius of this part is too long, you're gonna go ahead and decrease the pitch value, or the speed of the pitch change, and then increase the section like this. You can clearly see that the track is far away from the ground. It's the height of the section is at about 1.63 meters. So we need it to be a bit longer so that the train will be able to but notice what happened here. It shows a pretty high lateral force value. That means that our roll is larger than we need. So we're gonna go ahead and decrease the roll like this until it reaches something around 0. Yeah, 0.003 should be fine. From this point, you're gonna have to like adjust different points until it gets the desired shape, like this. Now we have reached a point really close to the ground, which is 3 meters, and that should be fine. What I've noticed here, I've been observing some photographs of this kind of roller coaster, and I would say that the roll starts like it starts around here, but it goes a bit longer around here. So we can go ahead and increase the roll section like this. But once again, you will have to adjust the value of the roll for the end part of your dive loop track not to have any laterals or nearly no laterals. Oh, I'm sorry, I was increasing the value. I have to decrease it. Decrease until this value reaches 0. So it has to be something like this. You can see there is still an X acceleration here, but you can change it later. Like you can establish this for a value that keeps this one 0. I think it looks like a fair dive loop drop. It looks pretty. We could have done it better, but it depends on, once again, depends on what you really want, which coaster you want yours to assemble the best. Let's just write it and see if it works as we desired. Unfortunately, we cannot see it as smooth as it really is because the recorder, like the program that I'm using to capture the screen, is a bit messed up. I don't know how to set the quality of the screen, like the FPS stuff. It has to do with something like that. But I would say this is a pretty good element. You can do it differently if you want. You can reduce the radius of this part right here, but it also depends on the height of your track. This one is pretty it's pretty high, so I assume this is a good element for this kind of coaster and the set height that we have up here. And I hope you guys enjoyed this video and subscribe to my channel, and I hope to come back with more videos later. This is the 4th tutorial. And that's it. Thanks for watching.